All right, recording is rolling. Welcome to Monday, April 17th. All right, we're going to take this week to study theory of relativity. So now this one you have to stretch your mind a little bit. There's some pretty non-intuitive concepts, but this is going to be an exciting ride. Right, so theory of relativity is really in two parts. There's special relativity and general relativity. I'm going to mostly focus on special relativity today. I'll briefly mention this other one near the end. Over the next few days, I got some problems I'll go over and solve with you guys. I've got some video demos, do some today, some coming days. All right, so let's get going. All right, so I want to start off with something that it's going to look like, well, it's going to connect. It's going to connect. All right. So I remember when I was studying for the FCAT way back in the day, you guys do like FSA or something, I don't know, they changed the name like every 5 years. Right? There's a problem that really intrigued me. Right? It involved a couple of guys who were in a race. Okay? And the way they're going to race is that they've got the start finish line right here. Let's call these guys Alan and Bob. Okay, so we got Alan and Bob. Okay? Say, hey, see that tree in the distance? We got this tree over here. Right? All right. So let's run from the start finish line. We're going to run around the tree and back to where we started. Right? Whoever crosses the finish line first wins. Okay? And they each have a different strategy for how they're going to run the race. Like they're pretty pretty similar runners that they usually tie, but they say, you know, we're going to try a different strategy here. Okay, so the speed of Alan for the first half of the race, he's going to go. Now these numbers don't actually make any like human sense, but it's just going to be an exercise. Oh, I forgot to give you guys distance. Let's throw a distance on here because I want to run the numbers and actually prove to you guys a certain point. Okay, let's call this distance 120 meters. Right, and Alan says, my strategy is going to be, I'm going to sprint to the tree as fast as I can, and then I'll pace myself back as fast as I can, but maybe it won't be as fast because I'm a little bit winded. So it's going to go 12 meters per second the first half. Yeah, I know it's crazy fast, but let's just run with it. Just an exercise, right? Okay. And then the speed of Alan for the second half, well, now he's winded coming back. Well, now he can only go like 8 meters per second. Right, so the second half. Right. Right. Now Bob has a different strategy. Bob's going to just pace himself the whole way at 10 meters per second for the entire race. Right. And when I say first half, second half, I'm talking about like distance-wise to the tree and then around the tree and back from the tree. Right. All right. So you guys get that premise. All right. So question is, who wins the race? Who's going to win that race? Alan, who sprinted and then came back a little slower, or Bob, who paced himself the whole way with that middle speed. All right, who wins that race? So a couple of guys working on the calculator, so yeah, give you guys a short time in case you actually want to get the actual answer. All right, so I'm going to see show hands. Maybe you just calculated it. Maybe you have an intuitive guess. Right? How many guys say Alan's going to win the race? Alan wins the race. Right? How many guys say Bob wins the race? Bob wins the race. Oh, yeah. All right. I'm seeing a bunch of hands go up. Yeah, you're right. Yeah. So you figured it out. Yeah. So some of you guys actually did the calculation, figured it out. So I'll walk through the calculation with you guys. So could you say that distance is equal to speed times time, right? And therefore, time is equal to distance divided by speed, right? And if you're looking to win a race, you really want the minimum time, like whoever has the minimum time to run this race, right? So let's see what their times are. Well, the time for Alan for the first half would be 120 meters at 12 meters per second, which is 10 seconds. Time for Alan for the second half is 120 meters back at 8 meters per second, which is like 15 seconds. Right? So the time for Alan total, 10 seconds to the tree, 15 seconds back, is 25 seconds. Okay. Right, now, if you look at the time for Bob, well, Bob ran the entire 240-meter race, 120 there, 120 back, right, at 10 meters per second, which is only 24 seconds. Ooh, yeah, so you guys are right. By pacing himself, Bob actually does win the race. Okay. Yeah, you can change this distance, that doesn't matter. If you change any of these numbers, you guys see like the average of 12 and 8 is 10, right? So part of what makes this work is the fact that when Alan was coming back slower, it's a long time that he's going slower, right? So it's not equal time slower, it's equal distance slower, but not equal time, right? Yeah, so takeaway, if you pace yourself, you'll tend to win the race, right? You see that? Okay. Now, what if I replace these guys running back and forth with, ooh, what if there's a river and there's like boats in the river and versus a lake? How about that? Okay. What if there's a lake? Let's have a lake here next to a river, right? And there's a couple of boaters, and one guy's in a boat here, one guy's in a boat here, so in the lake and in the river. One guy says, hey, I'm gonna paddle back and forth along the lake, and this guy says, I'm gonna paddle back and forth along the river. The river is in motion, of course, right? It's got some V, right? Okay. Who's gonna win that race, the guy in the lake or the guy in the river? Yeah, the guy in the lake, like for the same reason, right? Because he's like pacing himself versus the guy in the river. Maybe he goes downstream extremely quickly, and then he's like, it's a fighting battle all the way up, right? So yeah, the guy in the lake's gonna win for the same reason that Bob wins. Is that okay? Now hold on to the idea because that's gonna take me to I meant to mention something else first. Oops, that's right. That's right. My story's a little out of order, but hold on to the idea because that's gonna come back later. Right. So there was a question. There's been a question for thousands of years of what is the speed of light? What is the speed of light? Okay. And it was always assumed light has some speed. It does. I mean, other things have speed. Sound has a speed. It's been noted that sound has a speed, right? If you're like on a hill and someone else is on a hill like a mile away and you're yelling at each other, right? You can see it like a time delay, right? There's like a time delay, right? So, but what is the speed of light? Right? Is like 10 times, 100 times the speed of sound? Right? Wasn't known for a long time. In 1849, this guy named Armand Fizeau came up with this experiment to actually figure this out, and he did. He cracked the puzzle and actually got this accurately within about like 2% what the answer was. He said, well, you know what you do if you have this this cogwheel, right? And let's say you have this light source, right? And you have a mirror that's maybe several kilometers in the distance, right? Several kilometers. So this light's going to travel a long way there and back, right? And if I have an eyeball here to represent an observer, right? If you're like looking through these gaps in the teeth of the cogwheel, you can see the reflection of this light source, right? So it's reflected, great, you see it, it's all fine and good, right? But what if you get this cogwheel spinning? You spin it faster, 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 and at some speed, what's going to happen is this, right? Some of these incident rays will hit one of these teeth and never pass through at all, so their journey ends. And some incident rays will cross through the gaps between the teeth, bounce off this mirror, become a reflected ray, and come back. But if this cogwheel is spinning so incredibly fast that it's moved just enough, you know, maybe like a few degrees, so that the teeth cover the spaces where the gaps used to be, then now the observer is also not going to see that reflection, right? You won't see any of the rays that wouldn't have gone through in the first place, and you also won't see the reflected rays because now there's a tooth in the way, right? And what that looks like, suppose you're, again, like spinning this faster, faster, faster to get up to this special omega value, this angular velocity, right? It's going to look like a door is closing on that reflection. And right where the place where that door completely closes off and you can't see the reflection at all, right? That means that you've set up this cogwheel at just the correct speed to block the light. Therefore, you can calculate what the speed of light is. I did some equations over here. That'll lead you guys through it. I think this will be a challenge I'll probably throw you later this week, but you can calculate the speed of light that way. And it's a crazy fast speed. It's like 3 times 10 to the 8 meters per second. Right? That's what he found it to be. Okay? Okay. Now there have been modern updates to that sort of, but this is pretty accurate value. Okay? All right. So you guys got that? And so people know what the speed of light is. Now the next question is, well, what does light transfer on? Because like sound needs a medium. Okay? Like the fact that there's air in this room, you guys can hear me right now. If there was no air, I would just sound completely silent. Right? Or you know, you can like knock on something solid and send a vibration through, or like through water. That's okay too. But you need some kind of medium for sound. Now it was thought, you know, people are hypothesizing, you know, back in the 19th century. Well, let's see. Sound is a wave, needs a medium. Light is a wave. It probably also needs some kind of medium to go through. and they call that medium luminiferous ether. Okay, switch over to this one, luminiferous ether. Now, if you've never heard the term luminiferous ether, that's probably a good thing that it's not in science books, because it was uh, disproved with this particular experiment I'm going to walk you guys through in 1887. Unintentionally disproved, I should say. Right? So this team of scientists, what they actually were trying to do was to measure the speed of the Earth relative to this luminiferous ether that was assumed to exist. Like, it was just conventional knowledge. Well, oh, of course, there must be some luminiferous ether that is traveling, that allows light to travel on it, say from the sun to the Earth. Okay? And here's what they're thinking. Talk about model of the solar system here. So we got the sun, right? We got the Earth, right, going around the sun. Right? The Earth is spinning itself, right? At one revolution every 24 hours. I'll call that omega, right? Spinning, right? On its axis. Right? And if there's some luminiferous ether like out in the universe that allows light to travel on it, like as a medium, right? Well, sometimes, you know, just because of the spinning of the Earth, sometimes maybe we're traveling with it or against it, right? Or how about different seasons? Like if you're in the spring or in the fall, right? You'll be on different sides of the sun, right? The sun could be moving through the galaxy. It is. I don't know if they knew that at the time, but right. So you have all this relative motion. Right? You have all this relative motion. So just like the guys in the river and the lake, right? You should get different speeds of light depending on whether you're traveling with or against the luminiferous ether, right? Like if there is some ether and you're traveling with and against it, that would tend to slow you down. And let's say the motion of this supposed luminiferous ether was like perpendicular to the motion of light, then well, yeah, maybe it should like go. The light should be going as fast as it can possibly go, right? This is the model they had in their minds, right? You guys get that? Okay. Now, let's look at their actual experiment here. So let's have a light source, right? It'd be sending out rays in all directions, but maybe one ray could be like going in this direction, for example. We'll set up a mirror over here and a mirror over here, right? And right in the middle, we're going to put a 45-degree half silver mirror, which is going to act as a beam splitter, so that part of the light travels through it, and part of the light, boing, bounces off at a 90-degree angle. Right? You guys see that? And then bounces off this mirror, boing, and then travels back, and then also through, and then there's some kind of a detector or observer here. Right? Let's get that. Let's get this experiment. Now, if light traveled at all the same speed, then it should take the same amount of time, regardless of the journey. So if you go this way, boing, or if you go this way, boing, you should end up the same place, same time, right? That's not what they were expecting. They were expecting there to be different results. Let's say, for example, this is like an east-west axis right here. So the Earth is spinning along an east-west axis. It's going around the sun at, well, something like 20-something degrees to that, so not too far off, right? So anything that was east-west was assumed to be like trying to paddle with and then against a river, in which case it would be going kind of slower. Might take a while. There might be a time lag for it to reach this observer. Right? But anything that was like north-south, well, that would probably be perpendicular to that motion. So that'd be more like paddling around in a lake, right? Where maybe the medium's not moving, right? And so it was hypothesized that the light would show up at different times and therefore like be out of phase, right? You guys follow that? What they actually found was that the light was completely in phase, and it did not matter how they oriented this experiment, or what time of the day that they did it, or what time of the year that they did it. You know, different seasons, right? None of that mattered. They always got the light was always in phase, right? There were some other experiments that were like this too, which seemed to imply that the speed of light was always the same no matter what. Right? You guys got that? The speed of light is just the speed of light. And there is no luminiferous ether. Light can just travel through a vacuum. Okay, you guys got that? Now, they weren't expecting that. That was kind of strange. Right? But there's some really weird implications from this particular experiment. Right? So, what were the weird implications of this experiment? Think about this. We're talking about Newtonian relativity. Newtonian relativity. Okay. Now, when people say relativity, like just by itself relativity, they're not talking about Newtonian relativity. They're talking about Einstein relativity. But let's just start with something that we've been doing all year, right? Let's say you're in the back of a truck. Okay, so I got this truck. Okay. Let's say the speed of the truck, I'll do the truck relative to the ground. Right? So something relative to something. That's why I say relativity, right? What's moving relative to what? So the truck to the truck relative to the ground, let's call it like 20 meters per second. Okay. You're standing in the back here, and you take a ball and you throw the ball. The ball to truck is like 10 meters per second. So you can throw it 10 meters per second, right? You guys got that? Okay. But not only are you throwing it 10 meters per second, but you're throwing in a moving vehicle that's further moving 20 meters per second, all in the same direction. So if there's a guy out here with a radar gun standing on this grassy knoll, and he says, what is the speed of the ball to the ground? What's his radar gun going to read? How many guys say 30 meters per second? Right? Does that make sense? Right? It's being thrown at 10 meters per second forward. The truck's moving 20 meters per second forward. Add those up, get 30 meters per second, ball relative to ground. Right? That's radar gun reading. Okay. Now that's Newtonian relativity. Okay, so you'd expect that. Right. So all fine, good, nothing crazy. Okay. Now let's switch over to I'm gonna say Einstein relativity. And tell you guys about implications of experiments such as this one. Okay, so some really weird implications. Okay. So let's go back to this truck, except now we're not going to be looking at a ball being thrown around. We're going to be looking at the headlights and the speed of light coming from the headlights. So I'll say V beam, the speed of the light beam. Okay. Now I'll just call that C. So C could be the speed of light. Right? You guys got that? Okay. And let's say the truck has some speed too. So the truck to ground. So speed of the truck. Okay. Now I'm going to make a ridiculous number, but just run with the premise, right? It's just mathematical exercise. Okay. Let's say it's like half the speed of light, half C. Right? You guys got that? So right. Now, if you are inside this truck, right, driving the truck, right, then let's say you do some experiment to measure the speed of light of your light beam. So you break out that Fizeau cogwheel bubble, or however you do it. Right? You're going to measure the speed of light of your light beams as the speed of light. Right? What if you're outside the truck? So you're outside the truck, you break out the cogwheel, blah, blah, blah. You run the same experiment. Right? What do you think this guy says the speed of the light beam is? How about C? How about just the speed of light? Right? Right. Well, here's from a Newtonian perspective, you see why this would be a contradiction, right? In Newtonian mechanics, the velocities add. You add the vectors together. 10 plus 20 is 30. But whenever you're talking about the motion of, I'm saying light, but really it's all massless particles do this. Right? Anything is massless particles. Right? Anything that's moving at the speed of light is always, always, always perceived to move at the speed of light, regardless of what your own reference frame is. Okay? So it's not half C plus C is 3 half C. No. It's always C. Everybody agrees that the speed of light is the speed of light. Right? Okay, you guys got that? Okay. Questions so far? Right. Because that's a really weird idea, but it's going to open this up. Okay. So let's get to Isaac Newton, or Albert Einstein. Oops, Albert Einstein. Okay. So early 1900s, he's working in this patent office in Switzerland. So his job all day is to look at things that are mechanical, break things apart. How do things work? Has this ever been invented before? But right, and he's thinking about questions like some of those experiments that I was just showing you guys. Right, think about, well, what are the full implications of these things? Right, and he's asking questions like, well, what would it be like to ride along with a beam of light? Right, what would that look like? Right, and comes up with this thought experiment that involves this train, right? This train in motion, right? So there's the guy inside the train and there's the guy outside the train, right? They each have a different frame of reference. You guys got that? Right? Kind of like this guy inside the truck versus this guy outside the truck, right? It may be a different frames of reference, right? Right. And let's throw a light source like a flashlight on the ground. Right? And let's just have a light beam just go straight up and down. That's all the light beam does. Just boing. You guys see a mirror on top of the car, right? So that's all the light beam does. Boing. You guys got that? Right? Now, we throw in another idea. Right? goes way back. It's one of the first things I ever told you guys. Right, guys, if you're, can you feel how fast you are moving? Can you feel how fast you're moving? No, that's the correct answer. Correct answer is no. Right. Can you feel the Earth spinning right now? Nope. If you're blindfolded in the passenger seat going down 995, can you feel it going 50 or 60 or 70 miles an hour? No, right? As long as it's constant speed, you can't know that. You feel accelerations, you can't feel speeds, right? So this guy inside the train car, completely isolated from the rest of the world, he doesn't even know if the train car is in motion. All he sees is the light beam go boing, just up and down, right? Now, this guy outside the train car, maybe he's actually watching that the train car is in motion the whole time, right? So that same light beam doesn't just go up and down. That light beam actually travels like on a diagonal path. Wouldn't that be the case? Right? And the distance it goes would be something to do with speed times time, right? And okay, so speed times time would be distance moved, right? Now let's just look at this triangle right here. You guys see a nice right triangle right there? You guys see that right triangle? Right. So we can do like Pythagorean theorem analysis on this, right? So the distance that the train moves forward is the speed of the train times however much time has elapsed, right? In that T, notice I'm coloring it green. I do need to alter some of the colors on this page. I goofed up a little bit, but that's all from this guy's point of view. This is the guy outside the train is the only one who even knows the train is in motion, right? Sees anything about this horizontal motion, right? Sees VT is the distance the train moved, right? This guy inside the train says the light beam, let's just cut the problem in half, say like went up to the mirror, went the distance CT naught, and the guy outside the train says, no, it actually traveled along this diagonal path CT, right? The fact that they both agree on what the speed of light is, like if they both did some kind of experiment, they would both agree on what the speed of light is, C, means that the fact that these distances are different, but the speeds are the same, they have to be perceiving different passages of time. Right, you guys see that? So if they each have their own clock, right, the guy that's in the moving vehicle sees a certain passage of time, and the certain passage of time. The guy outside the vehicle sees a certain passage of time, and they're going to disagree about how much time that is. Right? The relationship is here. Here's Pythagorean theorem. You guys just do the hypotenuse squared is equal to the sum of the square of the legs of the right triangle. You guys can do that. Okay. Right, now I skipped a bunch of algebra steps from this box to this box. But if you solve for one guy's time in terms of the other guy's time, it ends up being this expression right here. Okay. You guys follow that? Right, now this red T naught refers to the guy inside the train, and this green T on the outside refers to this guy outside the train. Right? You guys see that too? Again, because they all perceive the same speed of light. That's what set up this whole thing. Okay? Right. Now, this whole square root in the denominator, this is called a Lorentz factor. It's going to show up in a few equations that they're about to follow up too. So this shows up all over the place. Right, now, let's think about this Lorentz factor, because there's some connections I want you guys to see. I want you guys to see how things go together, how things work, the bigger picture of some implications here. Suppose the train actually was at rest. Because if it's at rest, is there a problem? Or there should be no problem at all. Everybody agrees on exactly everything that happens if it's at rest because they have the same frame of reference. That means that this V would be 0. This V of the train is 0. Guess what is 0 divided by anything? 0. What's 1 minus 0? 1. Right. What's the square root of 1? 1. Ah, so T is equal to T naught. Everybody agrees on how much time has passed. It's all fine and good. Isn't that right? Right. Now, have you guys ever heard you can never reach the speed of light? Right? The speed of light is like a cosmic speed limit. Right? Now, truth be told, anything that has no mass always moves at the speed of light. Can't do anything else. Anything that has mass must move less than the speed of light. Right? What if something were to move at the speed of light? Right? Guys, what is c squared divided by c squared? 1. What's 1 minus 1? 0. What's the square root of 0? 0. What's anything divided by 0? Yeah, undefined. In effect, if you were approaching that from less than the speed of light, it would approach infinity, right? So it's like infinite time has passed, right? So like time would freeze for one person, and all of the universe would pass for the other person. Okay, right, right. Okay, right. You guys see that too? Right. So I want to take a pause here and throw in a video demo. So let me pause this video here and switch over and play you guys a demo.